Okay, so I'm live on YouTube. Let's just make sure, because yesterday it didn't quite go through, but I'm live, I believe right now. I'm going to go on Facebook as well. So give me a second. And it looks like the Facebook Live is working along. Okay. Connecting live video. And we are live. So good morning. Good morning on this, what is today? Today is Wednesday, June 17th. So good morning, and I had a call early this morning about a question, and I also did a presentation last night that talked a little bit about what I want to share with you today, and that is the breaker integrated transformer. A solution that can do a lot for electrical safety, solve some issues maybe with code-related issues because of some transformer requirements for disconnects and things of that nature. Just to give you an overview, there is a boom. Let's check this one out. I think that'll work. We have what I call the breaker what's called, not what I call, as we call from an Eaton perspective, the breaker integrated transformer. And I've got a call in 5 minutes, so this is going to be a very quick post. Breaker integrated transformer. What we did with this solution is we integrated, as you'll see right here, we integrated the primary and secondary. You can get this thing with just a primary breaker or just a secondary breaker or both. I'm going to give you some examples of why I think both of those give you some value. I personally am tied to the secondary breaker being tied into the transformer, and I'll show you why from a safety perspective here in a second. But this website, which the links are down below. If you're on YouTube, the links are down below, and Facebook, I don't know, they might be up above, they might be to your left, to your right. I don't know where they put it anymore. But in any case, there are some images here you'll see where we have the breaker that's integrated on the secondary and on the primary. We've got some good information, educational information on this site here that talks about this solution and all the different benefits that you get from the breaker integrated transformer. What I would like to just walk you through is the value that I see in this solution. And this slide is something that I use to help people understand on service entrance, but in reality, the first panel board on the secondary of every transformer has the worst incident energy because of this basic principle that I'm showing you here. The clearing time for the incident energy of the clearing time of the arcing fault current that would be in the for this secondary panel board. So if you're working in this panel board and you're doing the justified energized work, or if you again, if it's a service entrance, you got to call the utility to kill power. You may try to turn the breaker off here, but in reality, because of line side propagation, because of that plasma cloud that can occur inside this equipment, you could go phase to phase to phase on the line side of that primary breaker, which would mean the only clearing time is based upon that primary overcurrent device on the primary of that transformer, because that's your next upstream overcurrent device, and that transformer is doing something to you. And if you think about the issue that you have in this case from sizing this primary overcurrent device, you are increasing the size over the full load amps. You're not sizing it directly for the full load amps of the transformer. You're actually increasing it to a larger value. And the primary reason is no pun intended, the primary reason is because of the inrush current of that transformer. And what happens is you're putting a larger overcurrent device in. You got to move that instantaneous, add the time delays to let that transformer energize every time it is energized. And what that does is that adds an intentional delay. And when you think about an arcing fault in this piece of equipment, you're going to rely on that overcurrent protective device, which is not there to protect you in that downstream equipment. It is there to provide protection for that transformer and the conductors on the primary side of that transformer, and it is inflated in size. Now, a design principle to reduce the incident energy in this panel board, which would be a most common area that an electrical worker would do justified energized work, is to pop that main out of that panel board and basically relocate the energy into this enclosure, which would be much less of a likelihood of having to open that box than it would be getting into the main panel board that's on the secondary of that transformer, whether it's your service entrance equipment or downstream somewhere in your power distribution system. Now, what does just moving this overcurrent device out of that panel board do for the electrical worker from a safety perspective? I'm going to show you. Here's an example of a 250 kVA transformer. Because this breaker is integrated with this panel board on the secondary of that transformer, I'm relying on this upstream circuit breaker feeding this transformer, and my incident energy is 23.5 calories per centimeter squared. That's a big boom, all right? To knock that down, simply moving the breaker into its own enclosure or put a fusible switch in there, whichever you desire, simply making that move, I reduce the incident energy to less than 1 calorie. And that is daily wear. That is huge. If I put a fusible switch in there, I could take it down to 1/4 of a calorie per centimeter squared. So imagine taking this breaker, this overcurrent device, out of that panel board and then integrating it with the transformer. You kill a couple birds with one stone. You don't have an extra enclosure that you have to install. It's normally these panel boards are pretty doggone close to that transformer. I don't know if you've ever seen those. You'll see sometimes you'll see the primary panel, the transformer, and the secondary panel, because there's some requirements on the length of those leads and whatnot, the secondary transformer conductors. So this solution provides the ability to reduce the incident energy considerably in a panel board that is more likely to be entered to either do justified energized work or maintenance or things of that nature. I mean, just even if you established an electrically safe work condition, you still have to dress and get in there and put your test probes on to make sure you turn the right breakers off, you locked and tagged the right breakers off, and all that great stuff as per NFPA 70E. By pulling this out, you have a local disconnect right next to that panel board. And it could be a panel board, it could be anything. It could be a piece of equipment that you're supplying. Pulling that disconnect switch out offers a reduced incident energy, the more of a likelihood that you will establish an electrically safe work condition. And it's 8:02 and I gotta go. So this is the solution. I put some links down below. In addition to this PowerPoint, I'm going to discard those changes. In addition to that PowerPoint, I've got the design guide for you and a link to the design guide. Check it out. You could save a life, you could increase safety, and you could make your life more efficient by including this transformer in your designs. Thank you. Hope you have a good day. I've got to run, and have a safe day, have a healthy day, and stay out of trouble, all right? So I'm signing off. Thanks a lot. I'm ending my stream. Take care.